When you've completed this lesson, you should be able to convert back and forth between degrees and radians, those are angle measures in 2 dimensions, and calculate partial solid angles, which are angle measurements in 3 dimensions. Photonics technicians use angles in degrees and radians to make their calculations and their measurements. And so you'll need to be able to convert between those 2 measurements. And you'll note that 360 degrees is equal to 2 pi radians, and we'll work with that a lot in this module. You'll also calculate partial solid angles, angles that are measured in 3 dimensions, such as the solid angle that is subtended by a beam of light that emanates from a point source, spreads out, and the volume and the space that it encompasses is the measure of the solid angle of that beam. Here's an example scenario that photonics technicians have to work with. Laser light of 1.06 microns exits in laser through an aperture of 1 millimeter diameter. The beam spread of the light is through a circular opening of diameter d is given by the equation theta is equal to 1.27 times lambda over d, where theta is the beam spread angle, also called the divergence. And that's given in a radian measure. So we need to find the beam spread angle in both radians and degrees. Well, to do that, we'll have to learn a little bit more about angle measure, and so let's go and do that, and we'll come back and solve this problem in a minute. Well, you've seen angles and triangles before, like 60, 90, and 45 degree measures. These are all based on 360 degrees in a circle. Another common unit for angle measure is the radian, and that's based on the circumference of a circle. Do you remember what the formula for the circumference of a circle is? It's pi d, or 2 pi r. And 2 pi r is usually the more common mathematical way to do it because r is used in a lot of mathematics. But you'll see that we have corresponding to 45 degrees, and the measure would be pi over 4, or 1/4 pi, because corresponding to 90 degrees is pi over 2, and corresponding to 180 degrees is pi radian, and corresponding to 360 degrees is 2 pi radians. Just remember this, that a full circle has 2 pi radians in it. Now, how do you convert between degrees and radians? Well, first recall the value for pi is 3.1415926 and so on, but we always just refer to it as 3.14 because 3 significant digits is usually enough. But here it's more common when measuring angles to refer to it as simply as pi. You don't even need to know the number. Since 360 degrees is equal to 2 pi radian, or 180 degrees is equal to pi radians, we can use a unit ratio to convert degrees to and from radians, just like we used unit ratios to convert millimeters to centimeters and miles to feet, and so on. For example, let's convert 45 degrees to radians. Well, we'll use 180 degrees equals pi radians to form a unit ratio. We multiply by that ratio, pull out the values, and separate the units. The degrees will cancel, leaving us with just radians. And notice that we haven't put in the value for pi, but just left it as the symbol for pi. So we have 45 over 180 pi, or simply reduced to 1/4 pi. Example 2 says let's go the other way. Convert 3 pi over 2 radians, 3/2 pi radians, to degrees. Again, we'll simply multiply by the correct unit ratio to cancel the unwanted units. So in this case, you'll notice that we put the degrees on the top and the radians on the bottom because we want the radians to cancel. And so we group the values together, and this time the pi's will cancel. So we'll have 3 times 180 over 2 degrees, which is equal to 270 degrees. Now let's look at solid angles, probably something that's new to you. Recall that 2 rays on a pi define a plane angle, and you may have seen that in a previous module. The plane angle is the region on the plane that's enclosed by the two rays. So the angle measure is the measure of how far spread apart these two rays are. A cone in space is what's used to define a solid angle. So you can imagine this being a sphere, and out from the center of the sphere comes this cone. And how big this cone, or how much space is inside this cone, tells us the measure of omega, the capital omega, which is the symbol that's often used for the measure of the solid angle. Now, a point that radiates in all directions, so if we wanted to measure the solid angle of a point source of light, or a radio beacon, or something that radiates in every direction, then it would cover a total solid angle of 4 pi steradians. So in other words, if we weren't dealing with just a cone here, but if we took the cone away and said that the light could go anywhere, front and back, side to side, then the solid angle that corresponds with that would be 4 pi steradians. So the formula for doing that is the solid angle is equal to the area of the sphere, or part of the sphere that's intercepted there, divided by the radius squared, or how far away it is from the source. So that would be A over R squared. So for example, the solid angle defined by a whole sphere. We just figured out what that was in the previous slide, right? So if we had that whole sphere here, then what's the area of the sphere here? That's 4 pi times r squared, right? So the r squares will cancel, and sure enough, the solid angle by a sphere is 4 pi steradians, just as it should be. So if we have something less than a sphere, then we should be able to calculate the solid angle for that. So here's an example of determining the solid angle for determining less than a sphere. You have a point source of light that's 2 meters away from your eye, and we'll assume that your eye has a radius of 7 millimeters. The solid angle formed by the light entering your eye, that's what we'd like to find. So we've got the cone coming out from that light source, and when it reaches your eye, we're only interested in the 7 millimeter radius circle of the light that's actually going to enter the pupil of your eye. So all the rest of the light out here all around is not going to go into your eye. So only the light that's going to come right from their source and down that cone into your eye. So what we'd like to find out is what is the solid angle that's represented by that cone. So that would be pi times the radius squared divided by the distance squared. And notice that we've had to convert them to constant units. We've converted them both to millimeters. And the calculation is 3.85 times 10 to the minus 5 steradians. So your eye intercepts about 4 times 10 to the negative 5 steradians. So that's not a lot. That's only about 0.003% of all of the 4 pi steradians that are out there. So you can see that not very much of that light is actually entering your eye. So now we're ready to find the solution to that example scenario. So we have a laser light of a wavelength of 1.06 microns going through an aperture of a diameter of 1 millimeter. And we're asked to calculate what is the beam spread angle, what is the divergence, using this formula, 1.27 times lambda over d, and that'll give us a measure in radians. So if we substitute in theta equals 1.27 lambda over d, put in lambda, we'll convert everything over to meters so that we don't get confused in terms of the microns and the millimeters. We know that 1.06 microns is the same as 1.06 times 10 to the minus 6 meters, and 1 millimeter is 1 times 10 to the minus 3 meters. So that way the meters will cancel, and we'll have the two numbers to divide and multiply by 1.27, and the result is 0.00135 radians. But we don't have a very good feel for radians, so let's convert that to degrees. So again, we multiply that measure by radians by the unit ratio of 180 divided by pi radians. The radians will cancel, and the result will be 0.077 degrees. Well, that's a pretty small number, so the laser beam divergence is less than 1/10 of a degree, much less than a flashlight, for example. Now, let's look at the practice exercises in this unit. How many degrees are in a circle? So I'm sure that you already know this, but the answer is 360 degrees. Now, if a pie is cut in half across a diameter, and then each of those pieces is cut in half, and then each of those pieces is cut in half again, how many pieces do we have, and how many degrees do we have in each piece? Well, it's pretty easy to see that there's 8 pieces here. And so if we have 360 degrees is all of them, and then divided by 8, then each one is equal to 45 degrees. For the next one, how many degrees are between the 12 numbers on the face of the clock? As before, we know that we have 360 degrees on the whole clock, so this time, instead of dividing it into 8 parts, we'll divide it into 12 equal parts. And just one of those will be 360 degrees divided by 12, which will be 30 degrees. Now, how many degrees are there between 12 and 3? And you can see that just by looking at it. But just to be mathematical about it, since we know that one of those numbers is 30 degrees, so 3 of those numbers will be 90 degrees. So between 12 and 6, well, you can see that also without using a calculator. It's a straight angle, so it'll be 180 degrees. But if we go ahead and do the math approach to it, we'll say that there's 6 numbers times 30 degrees by each number, and that'll give you also 180 degrees. So how about between 12 and 9? Well, this one you may not have noticed before, but this is 9 numbers times 30 degrees, which is 270 degrees. Now to go all the way around from one 12 to another, we'll have to go all the way of 360 degrees. So you can do 12 times 30, again, 360. Now let's convert 60 degrees to radians. So again, we're going to take 60 and multiply it by our unit ratio of pi radians over 180 degrees. And we'll put 180 degrees in the denominator so that each of these 2 units will cancel. So then we'll group the values together, 60 over 180 pi, and we'll notice sure enough that the degrees will cancel, and we'll have radians as a result. So the numbers will simply simplify to 1/3 pi, or 0.333 pi. Now we're asked in exercise 5 to convert 5 pi over 4 radians to degrees. So again, we'll multiply by the correct unit ratio. We'll notice that it's a different unit ratio than the one up here because we want the radians to cancel this time. So again, we group the numbers. The pi's cancel here and the radians cancel. And we're left with the numbers of degrees, which is 225 degrees. Exercise 6 asks us to calculate the solid angle intercepted by a 4 centimeter by 6 centimeter meter, that is 1.5 meters from a lamp. So this is pretty much like the eye problem we had in the text. So here we have the formula omega, where the solid angle is over r squared, where a equals length times width of the mirror in order to calculate the area of that meter, and r is how far away the mirror is from the lamp. So we simply substitute in our expressions. A is L times W, which is 4 centimeters times 6 centimeters. And instead of 1.5 meters, we'll convert it in our head to 150 centimeters so that the centimeters will nicely cancel out for us. So 4 times 6 divided by 150 squared. And the answer is 0.00107 steradians. So the mirror intercepts about 1 millisteradian out of all of the 4 pi steradians that are available coming from that lamp, or in other words, about 0.08% of the light emanating from the point source. So it's always interesting to find out what percentage we're intercepting. Alright, well that concludes Module 9, Angle Measures in 2 and 3 dimensions. So I trust that you'll feel a lot more confident working now with angles, measures, and radians and degrees and steradians. See you next time.